Thank you. It's a great pleasure to be back. So on Wednesday, we did the physics of sentience, an introduction to the Bayesian mechanics that's going to underwrite the next two talks, which are more practical in nature and use the basic principles of maximizing a marginal likelihood, self-evidencing, maximizing model evidence, or minimizing a free energy, to understand how one can model and indeed build sentient creatures or artifacts that have this kind of action and perception. So this talk is going to be in two parts. One, setting up the basic ideas. The move in this talk is going to be away from continuous time systems that we used to demonstrate the sort of physics of sentience, and towards discrete state space models. So we're going to be dealing with models where you can be in one state at any one particular time, and furthermore, time unfolds discretely in steps. The first part of the talk is going to just review self-evidencing as a minimization of variation-free energy, and why that might be a useful perspective from the point of view of mathematical formulations of sentience and artificial intelligence. And then I'm going to take you through a worked example, a very simple example of sentient behavior to illustrate the nature of message passing in both simple schemes and schemes that consider planning and thinking about the future and what it means to minimize your free energy in the future. So let me just start by rehearsing the overall idea in relation to other global or normative brain theories. So we established last time that one fundamental dynamic, one apparent imperative of self-organizing systems that possess a Markov blanket is that on average, their dynamics appears to maximize the probability of their sensory states or observable outcomes given a Markov blanket or given a generative model of how those outcomes or observations were generated, and that we were associating perception with the optimization of internal states that stand in for the sufficient statistics or the parameters of some beliefs about the external states that are generating the observations. And in a similar way, active states or control variables, which in this presentation will be denoted by U, maximize exactly the same quantity. So how does that fit with other theories of self-organization and behavior? We already had a nice discussion about functional systems theory, and I could certainly try and put this in at some point, or perhaps you'll be more expert at putting this in. But let me just run through some of the other normative theories which you might be familiar with. So if these outcomes are the attracting sets that I aspire to, that I expect to occupy, the sensations I anticipate encountering if I am me, then they become attractive and valuable to me. So the log probability we can now associate with value. So maximizing the value is simply a restatement of the underlying ideas behind reinforcement learning, optimal control theory, and in economics, expected utility theory, all putting a teleology on this imperative to maximize model evidence. That's nice because the value is just the negative surprisal or self-information, or more simply surprise, in information theory. So if I now look at this log probability from the point of view of an information theorist, it's just the self-information, and it is bounded by the free energy. That means that I can now talk to and provide a mechanics that is synonymous with, say, the principle of maximum mutual information, the principles of minimum redundancy, and indeed, of course, the free energy principle when I use a bound on this surprise or self-information measure or quantity of observed outcomes. So that's good because the time average of self-information is entropy, which means that this maximization, this optimization reading of the this physics of sentience means that it'll look as if I'm trying to minimize the entropy or resist an increase in the disorder, effectively resisting the second law if it was a closed system. Of course, it's not closed because we have a Markov blanket, but one can certainly motivate an explanation of self-organization in terms of a resistance to disorder, a drive towards negative entropy of the sort seen in synergetics. And of course, if I was a physiologist, this would just be homeostasis, keeping my states within certain bounds. And the final perspective on this is the perspective of a statistician, that I am treating now this quantity as a probability of some outcomes given a model, basically the marginal likelihood, having marginalized out all the unknowns that are responsible for generating those observed outcomes. And then we have the Bayesian brain hypothesis, evidence accumulation, predictive coding, and so on. So that's self-evidencing in a nutshell. Its relationship to lots of established and very useful ways of formulating behavior. We've already seen the genesis of free energy. I'm writing it out here again using a different set of symbols, which are the symbols or the variables that people normally use when dealing with discrete state space systems. So O are the observations, S are outcomes, S are the hidden states of the external states of the world generating those outcomes, about which I'm forming approximate posterior beliefs denoted by the Q here. So we're dealing with probability distributions over discrete states. So as we've seen previously, the variational free energy is basically a negative entropy, energy plus an entropy here. And if I want to minimize free energy, then I'm if I want to optimize free energy, then in this expression, I'm going to maximize entropy, but it's the entropy of the beliefs. So I'll make another move here. Previously, we were talking about free energy, variational free energy from the point of view of a physicist. In machine learning, they actually switch the sign. So in this talk, we're always going to be maximizing a free energy. And that might be slightly counterintuitive because I've just said we're trying to minimize the expected self-information, but that's of the outcomes. That implies that we'll be increasing or trying to maximize the entropy of beliefs about outcomes. And of course, that's just an expression of James's maximum entropy principle, that any good set of beliefs should be those beliefs that commit in that give you the most latitude and don't commit to a particular explanation for some observations. So we have a maximization of the entropy of beliefs about the causes of our observations under certain constraints, here decomposed into the likelihood and the prior over those causes or states generating the outcomes. Just rearranging that, as we saw in the previous presentation, we can also express the free energy in terms of a bound on what? Well, on simply the log evidence or the log marginal likelihood. Why is it a bound? Well, because the difference between the free energy and the log evidence is a KARL divergence, which can never be less than 0. And it's just the divergence between our posterior beliefs that we're trying to optimize and the true posterior, which is the probability of the hidden states given the observations. So that's an important, I think, perspective, because if you were in artificial intelligence or machine learning, because you've got a generative model that defines all of these quantities, namely the prior and the likelihood, implicit in these equations here, then you have a way of explaining any beliefs or account or classification of the data at hand. So because you've got an explicit generative model, you have explicit or explainable and interpretable artificial intelligence. You've also got a degree of design optimality. And I'm going to emphasize the abductive aspect in terms of Bayesian inference, but also, as we'll see later, the ability to go and acquire the right kind of data that underwrites that abductive inference. So we have a sort of Bayesian optimality for free simply by optimizing this evidence bound. So in machine learning, this would be known as a lower evidence bound or an evidence lower bound or an elbow, because we're working with the negative of the physicist's free energy here. As we'll see in the next slide, or in a couple of slides, we can actually go beyond just making Bayes optimal decisions and forage for data in an optimal way. But that does rest upon a particular on a particular extension. But before we go there, let me just rearrange. All I've done is just rearrange the terms in this expression to re-express it in terms of accuracy and complexity, which is the way that a statistician would partition or decompose this free energy functional, where the accuracy is just the expected likelihood, not the marginal likelihood, but the likelihood of some outcomes given their causes. And the complexity is just the KARL divergence between the posterior beliefs and our prior beliefs. It's literally the amount to which we change our mind given some new sensory evidence. It's the cost of belief updating. And in maximizing this, we want to minimize the complexity, and that is just an expression of Occam's principle, finding the simplest explanation possible that still affords or gives an accurate account or explanation for the data. It's an interesting term because you now have a way of evaluating the computational cost under certain prior beliefs, which means that you've got a kind of bounded rationality that leads to, as we'll see when we're using the free energy, an approximate Bayesian inference that rests upon priors. Sometimes people can think of this in terms of heuristics, but ways that simplify the way that you try and explain the causes of your sensations or outcomes. This computational cost actually has, via the Jasinski equality and Landauer's principles that say that to erase a bit of information costs a certain amount of energy. You can write down the belief updating implied by the complexity in terms of the joules that it would take, or the amount of electricity it would take. So minimizing complexity really is saying that if you're doing it in an optimal way, you should be able to process some information, do some calculations as quickly and with the minimum amount of energy as possible. And that is that is a direct consequence of Landauer's principle when formulating optimal behavior or sentience in terms of a mixture of accuracy and complexity. So the big thing that I really want to talk about here, though, is, well, that's fine in terms of describing what is optimal in the moment, in terms of making sense of data at the moment. What about the way that we behave? What about looking at behavior as the way in which we go and choose and sample new data? What are the principles that would underwrite the optimal sampling of new data? Now, those principles have been known for a long time in the context of Bayes optimal design, the right way of designing experiments in science, for example, that resolve your uncertainty about the null hypothesis versus the alternate hypothesis. And it transpires, in fact, the whole point of this talk really is to bring to the table the insight that the expected free energy following a particular policy or act now becomes the expected accuracy that enables you to understand good behavior, self-evidencing, free energy optimizing behavior in terms of optimal Bayesian design, while the complexity actually becomes something called risk and underwrites or underlies Bayes' optimal decision making. And the mixture of these two expected accuracies and complexities expected following an act upon the world then becomes self-evidencing. So self-evidencing optimizing free energy can be unpacked into or divided into these two kinds of Bayes optimality. So let me now motivate that more from first principles by asking a question. So I want you to imagine you're an owl and that you're hungry. And if I were able to talk to you directly, I would be asking someone in the audience, what are you going to do? And then normally someone would say quite correctly, well, I'm going to search for my food. I'm going to fly around until I can identify the location of my food, and then I'm going to eat it. And they will be absolutely correct. That answer has some fundamental implications. Implications for what? Well, for the way that we write down what is optimal behavior. And we've got two choices. One, which would be probably the more conventional approach, would be to assume the existence of a value function of some states of the world if I took this action U at time t. And if I were able to identify the action that maximized the value of the state, then I would have a state action policy. Is that going to work for us? Well, possibly not. Why? Well, because when you search for food, searching is an action that minimizes your uncertainty about where the food is. But uncertainty is an attribute of a belief about states of affairs. In this instance, a Bayesian belief, our Q, our posterior belief about the states of affairs given a particular action. So that suggests that the right kind of optimization should be not a function of states of the world, but a functional of states of the world, where it's a function of beliefs about states of the world. And furthermore, the order in which I do things matters, in the sense that if I try to eat my food and then search for it, I will have a very different outcome than if I searched for my food, located my prey, and then ate the food. So we really have to consider the order, the sequence of actions, which I'm denoting by pi here, that maximize some functional of beliefs about states of the world under some plan or policy pi. And of course, we're going to use the expected free energy as this functional to give us now an optimal policy that can be expressed as a path or time summation or integral of an energy function. And in physics, that's an action. And I phrase it like that because we can now compare and contrast these two approaches. These approaches, these state action policies, are based upon Bellman's optimality principle. And you may be familiar with those in terms of optimal control theory, dynamic processing, deep RL, expected utility, Bayesian decision theory, and the like. Whereas this is simply a statement of Hamilton's principle of least action, or a variational principle of stationary action that includes the free energy principle, active inference, and crucially, as we will see, things like artificial curiosity, and in robotics, intrinsic motivation, the intrinsic value of reducing uncertainty and searching the world in a particular kind of way to resolve uncertainty about what will happen if I do that, or if I open that door. And those are the principles that underwrite the scientific process, experimental design. So they can also be understood in terms of optimal Bayesian design and the sequence of moves or plans that you have to move through in order to comply with this principle of least action. And we're going to unpack that in terms of partially observed Markov decision processes. I have deliberately introduced this sort of formal distinction between Bellman optimality principle based approaches and Hamiltonian or principle of least action based approaches, just to make the distinction very, very clear. However, what we'll see later that we will repair this difference, and we'll actually see that this is a special case of this when there is no uncertainty. So that's where we're going to go next. So here's the overall architecture that we have in mind from those considerations, where we have a Markov blanket with our sensory and active states here. The active states go and change some external states that supply some observable sensory outcomes. They are then used through perceptual inference to optimize our beliefs about states out there by maximizing this free energy functional or function of states, a functional beliefs about states that has the accuracy and the complexity parts to it. And then we use these beliefs to evaluate the goodness of a policy in terms of its expected free energy, the free energy that you would get if you committed to this particular policy. And it's just the expectation of these quantities under the predicted outcomes if I pursued this plan or policy. And that expected complexity becomes risk and accuracy becomes ambiguity. And I can score every policy with an expected free energy, and then I can choose the best policy, select the next action, and then the cycle continues. So here are the same expressions. What I want to do now is just, again, try to relate these to normative theories, teleological theories that are already established and work extremely well in terms of describing behavior and the way that we act and perceive. And I'm going to do that just to again highlight this nice symmetry between the variational free energy and the expected free energy that we can decompose either in terms of complexity and accuracy, or from the point of view of machine learning, into log evidence and its bound to give us an evidence lower bound. And then we just take all of these expressions and take the expectation under the predictive posterior over outcomes, and then the complexity becomes risk, the accuracy or the inaccuracy becomes ambiguity, the log evidence becomes an extrinsic value, and the evidence bound, the KARL divergence that we want to minimize, becomes an intrinsic value that paradoxically we're going to be maximizing, and I'll explain why in a second. So what is intrinsic and extrinsic value? Well, let's just ignore extrinsic value for a moment and just look at this term here. So what is this term? It's a KARL divergence between beliefs about states of the world in the future, given a particular policy, with and without the observations. So effectively, it's an information gain. It's an expected relative entropy or KARL divergence that scores the information gain, the degree to which I have changed my mind. So it's expected complexity. But this is now good because the outcomes are now random variables because I haven't yet seen them. So this Bayesian surprise, this is the name that is found in the visual search literature in the neurosciences, scores the information gain that, or the reduction in uncertainty, also known as epistemic affordance, of this particular policy. And mathematically, it's just the mutual information between the causes and the consequences given in the future, given a particular policy, and related very closely to the principles of maximum mutual information of people like Horace Barlow. So that's what intrinsic value is. It's the epistemic affordance. It's the ability to reduce uncertainty about states of affairs in the world if I sampled, if I were able to sample these observations with this plan. Let me now take a certain kind of uncertainty away And the uncertainty I'm going to ignore now is ambiguity. So I'm going to pretend that there are certain artifacts, there are certain systems, robots, that can see directly all the hidden states of the world. So there's a one-to-one relationship between the state of the environment and the observed outcomes. So the O's become the S's and there is no ambiguity. And we're just left with this term here, which is another KARL divergence. It's another difference between probability distributions. And in this instance, it's just the difference between what I anticipate the state of the world or the outcomes will be given a policy or a plan, and what a priori I prefer or expect to happen. So these probabilities, if you remember, describe the kinds of states that I will anticipate experiencing or encountering, those that are attractive to me. So this is just the difference between what I think will happen if I do that and what I want to happen. And this is just a mathematical expression of, in engineering, KL control under some prior preferences. In economics, it's known as risk-sensitive control that tries to minimize the divergence from prior preferences. So let me now take the last kind of uncertainty away, which is the risk. So it doesn't matter what we do, we're always going to have the same kind of risk, the same kind of prior preference. So what are we left with? Well, we're just left now with the extrinsic value, which of course is just the value that we talked about on the first slide. It's the expected log probability of my preferences. And this is exactly what the Bellman optimality principle tries to optimize. In economics, it would be known as expected utility theory. So as I promised earlier on, we've now got back to a description of optimal behavior that is compliant or to which you could apply the Bellman optimality principle. But to do that, I've had to remove all sorts or all the different kinds of uncertainty from the problem. So in this sense, the Bellman optimality principle can be seen as a special case of the more general principle of least action that arises when there is no uncertainty, and in particular, there's no ambiguity or intrinsic value available that would guide our decision making. So to put that very simply, what we're talking about is that if active inference is the optimization of the expected consequence of an action expressed in terms of an expected free energy, then we can divide or decompose that into two components. One, the expected value, which would be associated or would be the kind of optimality that is considered in Bayesian decision theory, leading to Bayes optimal decisions, and the information gain. And this is the kind of Bayes optimality that you would see in the principles of optimal Bayesian design, and indeed the kind of principles that we actually use as scientists to design our experiments, the two together being expected free energy. So let me now end this unpacking with a number of examples and how you can use that calculus to build little artifacts and see how they behave. All of this rests on a generative model. And by generative model, I just mean a way of writing down the probability distribution over the knowns and unknowns, the known observations in the past, sometimes unknown in the future, the states of the world generating those, and the unknown policies. We have to infer, we have to plan, therefore we have to infer our policies so they become unknowns as well. So I just write down a generative model, and then I can invert that model because that model defines the free energy and the expected free energy, and I can then just minimize that. A particular way of doing that, or a very generic way and a very efficient way of doing that, is to write down your probabilistic generative model as a probabilistic graphical model. So the kinds of models which I'm going to use to illustrate these ideas are Markov decision processes. They're very simple, They just say that the state of the world can be written down as a very large vector, possibly factorized, and exists at any one, the world exists at any one state at any one particular time. And then, according to some probability transition matrix, it transitions to a new state. And that transition depends upon the policy. And the policy depends upon the expected free energy. If I know the state, then I have a likelihood mapping that generates outcomes. So we're going to denote the likelihood mapping, or it is usually denoted by a tensor or a matrix A, leaving as priors in the model the parameters of the probability transition matrices and the initial states, and of course the expected free energy being a hyperprior that determines the best policies. So that's my generative model written down as a graphical model. If I can write down a graphical model, then there always exists a factor graph, a normal style or a Forney, F-O-R-N-E-Y style factor graph, which has a different construct, but a very useful rewriting of this kind of format. So in factor graphs, so it's certainly in the normal style factor graph, the factors of the probability distribution that constitutes my generative model now become the nodes. And then the variables, the unknown, can be associated now with the edges so that we can understand how factors depend upon the messages that are passed from one factor to another factor. And that's very useful if you're a computer scientist or you try to write down some code that would invert this model, given some observations here, because you can work out very simply using simple off-the-shelf rules what these messages should be that enable you to invert or optimize your posterior beliefs about all of these unknowns. So I've just written down you can ignore these equations. They just basically define the generative model that I've just described here in terms of categorical distributions, and with a particular approximate posterior where I can say factorize the succession of beliefs about posterior beliefs about different states into states at each point in time. I can now evaluate these messages and write down belief update equations for everything that I don't know. So for example, well, in fact, the only things I don't know are the states of the world and what I'm going to do, the policies. And the policies are just a simple softmax function of my expected free energy. And the states of the world become essentially mixtures, a nonlinear function, a sigmoid softmax function of linear mixtures of states or belief expectations about states in the past and the future, and the evidence from the current point in time based upon the outcomes. And this is the expression of the expected free energy with our risk and ambiguity terms here. And then I simply select the outcome, or actively select the outcome that minimizes the expected free energy. So that those are very, very simple updates. And I repeat, there's nothing magical about them in the sense that they are just off-the-shelf standard variational updates that inherit from being able to write down the factor graph that itself inherits from specifying the generative model, in this instance as a Markov decision process. So I've just written down those belief updating or message passing equations again, just to observe, if you didn't know this, if you don't do neurobiology, it is remarkable how similar these updates are to what happens in the brain. So the unknowns that we have in play are the hidden states that can be thought of as nonlinear sigmoid activation functions of linear mixtures, which we can regard now as connections in the brain of past and future representations and the data, the sensory inputs. A policy selection becomes a classical softmax function of expected free energy. I've actually equipped this model with a precision or temperature or sensitivity parameter just to balance evidence from the past about policies and my belief about their goodness in terms of the future consequences scored by the expected free energy. And the inverse of this is known as a precision of beliefs about policies. And the reason I've done that is that it looks as if that plays a very important part of action selection in the brain, and may be encoded by dopamine in the brain in the form of a prediction error or a reward prediction error, where reward here is read as expected free energy. The updating the parameters themselves looks very much like associative plasticity or Hebbian plasticity. It's here just shown for the initial states. Effectively, all you're doing is accumulating instances, co-occurrences, and building up the parameters of your beliefs about the parameters of the generative model, the likelihood parameters, and the transition parameters in the form of Dirichlet parameters or concentration parameters of a Dirichlet distribution. And then action selection is selecting the best action from my favorite policy. And once you've got these equations, you can start to think about, well, what would that look like in a brain? And indeed, it's a story one can tell. I won't tell it here. It's an interesting story and game, trying to associate all these updates and representations with connections and specialized brain regions responsible for processing information, selecting actions, getting the precision or the confidence in your plans right, and then sending executive predictions to the motor cortex so you can act to generate some new data. So here's an example using exactly those equations. So we're now solving the equations, these discrete updates in a biologically plausible way, to emulate this sort of optimal behavior. The illustration set up here is a two-step maze task. It's a two-step task because this little mouse can only make two moves. It starts off in the middle, and it wants to secure or get this red reward, but it doesn't know whether the reward is on the left or on the right-hand side. It's also got another choice here, because what it can do is it can go and look at this instructional cue, which tells it whether the reward is on the left or the right-hand side. But because it's only got two moves, it's got a choice. It can either take a chance and go to one arm or the other arm, and if it goes there, these are absorbing states, so it has to stay there, and half the number of times it will be successful, and the other half it won't. Or it could use one of its moves to find out where the reward is and then go straight there. So from the point of view of the expected utility, the two options have the same outcomes. But from the point of view of the expected free energy, it's going to find the moving to the instructional cue much better, in the sense that this has an epistemic affordance because it has an information gain. So here are the priors in terms of the probability transition matrices, and here's the likelihood mappings in terms of what it will actually see in terms of locations and outcomes, whether there's a reward or a cue here. You can write down this generative model in a very simple way and apply those equations, and then just iterate those belief updates and learning to see how the little mouse behaves. And as we would anticipate, it starts off by always going to the conditioned stimulus or the instructional cue, and then going and getting its reward because it now knows where to go. And I've illustrated that here in a series of formats. These tell you where the reward was. Was it on the right or the left, or the right or the left? This panel here shows the policies. Shall I stay here? Shall I and then move up there? Shall I go over here and then go back? Shall I go down there and then go to this arm or go to that arm? All of these are alternative hypotheses that the agent is evaluating in terms of the expected free energy, and then choosing the most likely one, which is either policy number 9 or number 8 in the first few instances. And these are the outcomes, whether the agent was successful or not, and how long the reaction times it took to do the belief updating and secure the rewards. This is the learning. The learning here is initial state. Was the reward on the left or was it on the right at each trial? Now, what I've done here, what we have done here, is after the first few trials, we have left the reward on this side, so that as time goes on, the mouse starts to learn that the context is always a left context. And that has an important consequence, because the epistemic affordance, or the intrinsic value, or the information gain of the conditioned stimulus starts to decrease, because it has less and less information the more the mouse believes it knows where the food or the reward is. And at some point, the intrinsic value becomes less than the extrinsic value of simply going straight to the reward. And here at trial number 20, there's a shift in behavior from explorative behavior to exploitative behavior. So where the mouse goes straight to the reward here. So this illustrates something you see ubiquitously whenever integrating this or doing this kind of belief updating, that there's a natural progression from exploratory behavior, where you're responding to intrinsic values, epistemic affordances, to resolve uncertainty about the context in which you are operating. And once you've resolved that uncertainty, there is no longer any intrinsic value, and then the extrinsic part takes over and you start to become exploitative. So a move from epistemic to more pragmatic or utilitarian foraging. And this all rests upon accumulating evidence and learning and becoming familiar with the environment. So I'm now going to finish with an illustration of that basic mechanics, but in a slightly more interesting generative model. This is a repeat of the previous slide. If you remember it, this describes a Markov decision process that is special in the sense that the policies are a priori determined, or the log probability of different policies becomes the expected free energy. This is the probabilistic graphical model and the corresponding factor graph that prescribes for us our message passing, or our belief propagation, or our belief updating. What I'm going to do now is ask, well, what about breaking this Markovian aspect of the generative model and acknowledging that in the real world we're dealing with non-Markovian dependencies that unfold on many different temporal scales? How would I articulate that in a generative model? Well, it's very simple to do. All you do is you put another Markov decision process on top of a lower Markov decision process. And crucially, this Markov decision process unfolds, or the state transitions occur more slowly than the lower Markov decision process. So for every, say, 3 transitions at the lower level of this deep and diachronic generative model, there's just one step or one transition at the higher level. So we now have a semi-Markovian process where the higher, slower process generates the context or the initial states for the fast process. And if I now convert this generative model into a factor graph, it nicely illustrates the kind of belief updating in the sense that previously, from the point of view of the generative model, we're generating a succession of slowly changing contexts and initial conditions that enable a fast rollout and dynamics and trajectory at the lower level that then switches to a new context, and then we repeat ourselves. From the point of view of the message passing, that means that when we're inferring the context, we're actually taking the accumulated evidence that is very quickly assimilated by the lower level from all the outcomes and prior beliefs about fast transitions to accumulate all that evidence in the form of messages that now allow us to recognize the context we are in. But of course, we also have prior beliefs about what the next context is going to be. So we have now a deeply informed generative model simply by making it hierarchically deep, by putting a slow Markov process on top of a fast Markov process. So I would want to just illustrate how you can use that to understand how we as sentient creatures assimilate information in a really efficient way in accordance with all the principles that we've been talking about in terms of optimal Bayesian design. I'm going to illustrate that using a model of reading. So a very simple kind of reading where the words are composed of little letters, here icons. So the letters that the agent sees at the faster, slower level are pictures of birds and cats and seeds and blanks here. And these letters, when it's looking at a particular corner of the word, corner 1, 2, 3, and 4, and it knows which corner it's looking at in terms of the where it is looking at the word, are generated by these hidden states here. So these are the things it has to infer, which have both the what and the were aspect. So these hidden states are basically, these letters are generated by one of three words. Flee, which means that there's a cat near a bird. Feed, which means there's a bird near some seeds, or just wait when there's nothing next to the bird. So these can be thought of as words. If I knew the word and I knew where I was looking, I would know which letter I was seeing. Just to make things interesting, I'm also going to just flip these icons. You can think of this as presenting a word in a different font. So this is the lower level model, very simple. It's just saying that I'm generating letters from words that have a particular location in a word to produce outcomes, basically what I'm seeing and where I am currently looking. But where do the words come from? Well, they come from a higher level. They come from a succession of words that constitutes a sentence. And in this simple model, there are 6 sentences that could be like little stories or narratives that are, for example, flee, wait, feed, wait, or wait, 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 and feed. And these words are put together in a sentence, and I can also look at the next word or the next word, or could go back and look at this word here. So provided I know which sentence I am currently looking at and which word I am looking at, I can always generate the word currently being examined or visually palpated. And when combining that with where I'm looking in the word, then I can generate my outcomes. So we've got these 2 generative models, if you like, one at a higher level that generates the initial conditions or the context for the lower level that allows me to generate the sensations that underwrite or subtend reading. If I now write down the factograph and take out the message passing and integrate that scheme, this is the kind of behavior that we see. So what I'm showing here is a little agent who's reading this sentence, flee, wait, feed, wait. And here are the words. And this is where she's looking. She's first of all looking at the cat and then jumping to this location in the next word, looking at this letter, which is a blank, and then saccading over here, and then saccading or looking using fast eye movements, saccards to the next word, sees this, and then moves on. This is an equivalent representation of this, showing the time-dependent belief updates in terms of the posterior expectations or beliefs about the actual word and the sentence at the higher level, the second level expectations. And the interesting characteristic of this simulation is that it reproduces exactly what we do when we read. So we don't look at every word, and we certainly don't look at every letter. We just go and sample those informative bits of information which confirm our prior expectations, or certainly disambiguate in the sense of resolving uncertainty about what things could be. So, for example, as soon as this synthetic agent sees a cat, she knows immediately it has to be a flea because it can't be any other word. So she moves straight away to the next word without bothering to saccade around the current word. So skipping things that are not informative, that have low intrinsic value from the point of view of the expected free energy. And because there's no extrinsic value here, the expected free energy is just the intrinsic value. It's just the information gain that is driving all the behavior here. So this is another way of looking at those results that I'm showing to illustrate this diachronic aspect of belief updating at different temporal scales, which is very interesting because it reproduces the sort of patterns of belief updating we actually see in the real brain. So here, what I've sketched out or illustrated is the posterior expectations about the word at the lower level and the sentence at the higher level. And what we see is that very quickly we assimilate evidence by saccading around, looking at different letters, assimilate evidence and perform very confident posterior beliefs about the letter. Then we move to the next word and we form confident beliefs about the next letter, and then slowly accumulate beliefs about the sentence at the higher level here. And what we see is, because the only thing that distinguishes between sentence 1 and sentence 4 is the last word, then uncertainty, ambiguity about the sentence is only resolved right at the end, when this agent actually forages and recognizes the very last word to correctly infer that the top sentence was indeed the sentence that she was reading. I've used this format because it's very similar to patterns of activity we see in the brain when in this instance, monkeys are performing similar tasks. So here is unit activity recorded from brain cells during a pre-saccadic delay period activity, saccadic being an eye movement, pre-eye movement delay period activity in the prefrontal cortex, and shows a very similar pattern of evidence accumulation during this visual palpation or this visual search that we are simulating just by iterating these belief updating or belief propagation equations. Similarly, if I were to take this time series here and smooth it and filter it, I've now got a way of generating synthetic local field potentials or electrical signals that we can record in the brain. So I've superimposed the belief updating and simulated local field potentials for the higher and the lower area here. And they're remarkably similar to that which we see empirically when looking at perisaccadic around saccade field potentials during active vision in a lower area and a higher area of the monkey brain here. So that's, if you like, a nice illustration of the potential construct validity of this kind of belief updating based upon self-evidencing, more specifically, choosing those acts that maximize our expected evidence or expected free energy that can be unpacked in terms of optimal Bayesian design principles and optimum Bayesian decision principles. And all of this inherits from this decomposition of the marginal likelihood or the evidence into accuracy and complexity, so that to self-evidence means that we are trying to provide an accurate account of our sensory inputs in a simpler way as possible. So essentially everything should be made as simple as possible, but not simpler. And with that, all that remains is for me to thank those people whose ideas I've been talking about. And again, thank you for your attention. Thank you very much indeed.